All right, it's 1 o'clock. How are y'all doing? Well, yeah, I think it's 1. Yeah. How are y'all doing? All right, y'all have a good weekend? Okay, so we are continuing what we did last time, which was sketching polynomial functions. And I was looking at our schedule, right? Today is the 11th, right? So we're supposed to be starting properties of rational functions. We are not. We're going to continue with the real zeros of polynomial functions. Everything I have clumped up here together, I'm not following the book. I'm just kind of doing it the way that I like to present it, as opposed to following this book method. So all the homework for these sections I've removed from our online system, and anything I want you to do here, I'll give you it in class, just like I did last time. And then we are not going to cover at all the complex zeros, or what's called the fundamental theorem of algebra. And this is kind of like, if we have time, I'll cover it, but I want to give you an idea of why I'm not doing it, okay? I don't want to just like scratch it out and be like, yeah, we move on. And here's the reason why. When it comes to the complex numbers, we only talk about them briefly in college algebra. We just introduce the idea of a complex number, and then you don't see it again at all. You don't see it in pre-cal. You don't see it in Cal 1, Cal 2, Cal 3. Nowhere in calculus do you actually encounter complex numbers again, unless you take a class later, a math class called complex variables. So you have to take like linear algebra, differential equations, get through all those, and then you finally we'll talk about complex numbers. And the reason why is because you actually have to have 4 dimensions in order to visualize the functions, which is very hard for students to do. So you have to have gotten yourself to a pretty high level, like mathematical maturity level, to be able to handle 4-dimensional functions. So I don't think we can, it would almost be like me just like opening the window, letting you peek in, close the window, you don't see it again for years and years and years. So when you get to that point, if you do, depending on your major, if you do get to complex variables, I think by that time you'll pick up the basic stuff really fast. It's not difficult. So, okay, so that is officially off our schedule. And so today I am going to finish up the real zeros of polynomial function, and then next class we'll do rational functions. And sorry, yeah, the next class. I'm not sure how this is going to go. We'll see. Your exam 2, I'm going to keep this date, October 20th, which is next Wednesday, right? Yeah, next Wednesday will be your next exam, which will be here, face to face. And it'll cover, well, let's talk about what it'll cover when we finish on Wednesday, because exam 2 will only cover up through what we do this week. Okay, Monday of next week, whatever I do will not be on exam 2. So let's just stand by before I tell you exactly what's going to be on that test. Any questions on that? Yes. Will it be a bonus question about what we did on? Yeah, I may, depending on what we do. Well, the problems we're going to be doing are so long. These rational functions, graphing them takes so long. To put it as a bonus question, I don't know. I mean, that's like a 20-minute problem perhaps. So I don't know. I might do something where there's bonus material or bonus question off of something. Anything else about the test? Review? Are we going to have a review? I plan on having a review. So I should be able to get you that review, by the end of the week, and at least you'll have it for the weekend. All right, something is going on. Very, very, very strange here. All my notes have disappeared. So I'm going to close that program and reopen it. Last class, we were having all sorts of issues with the projector, weren't we? It was flashing on us, doing some weird stuff. All right, everybody at home can hear me and see the screen and everything's good?
Yes, sir.
Okay, thank you. All right. So when we were here last time, we were going, I think the first problem we did, we were trying to graph something, and remember it didn't factor. Remember that problem? And we kind of got forced down this road, right? We got forced down this road where I had to show you that whole synthetic division thing. And I asked you, do y'all want me to show you? And y'all were kind of like, yeah. Well, now I'm going to like formally show you what it's all about. And then we're going to do, my goal is for us to be able to graph 4 rather nasty polynomial functions today. And we're just going to use the steps that we learned last time, which is, determine the end behavior. So use that table, find the x-intercepts. This is the hard part. And then check out the multiplicity on each of the factors for the bouncing and crossing. And then we'll just go ahead and sketch. So, all right, here we go. So this is stuff out of the book. This first theorem out of the book is called the division algorithm for polynomials. And this is actually, I wanted to include it. I don't want us to get bogged down on it because we're actually not dealing with rational functions right now. We're not doing a polynomial divided by a polynomial. This will come up later. So I wanted to just put it in the notes so I have it. I want us to just not really think about this right now. I want us to be looking at the next major theorem, which is called the remainder theorem. And this is the part that we use for synthetic division. The remainder theorem says, suppose f is a polynomial function. If we take f of x and divide it by x minus c, then the remainder is f of c. Okay, this is a theorem. So I'm not going to prove this theorem. I'm just going to show you how it's used. So we're going to just start with this first little example here. And let me go ahead and put it down. And then I'll refer back to the theorem so you'll understand. Hopefully, when I go back to the theorem, you'll be like, oh, now I see how the theorem works here. This is actually a very, very powerful theorem. So it says here, find the remainder when you take this function and divide it by these two things. So we're going to do these one at a time. So let's do part A first. So for part A, what we want to do is take x cubed minus 4x squared minus 5, and we want to divide it by x minus 3. Okay? And then figure out what the remainder is. Okay? Figure out what the remainder is. Now, when we go to divide this, we have 2 options to divide. We have what's called long division and synthetic division. We talked about synthetic division last time. We're going to do both right here. Okay, we're going to do both. We're going to start with long division. Now, does anyone remember what I told you? I think I mentioned last time, kind of like the pros and cons of each one. Like long division is good, synthetic division is good. I don't think I mentioned. Never mind. Just hang tight on that. Let's do long division first. Long division, everyone, I don't know why, everyone hates long division. Not sure why, but it's a very useful skill. You use it in Cal 2 quite a bit. We do long division. So when you're in Cal 2 and you get to it, it's like, we don't reteach it. You just go and do it. So let me go through. I want to just, kind of inspire the idea. The idea is to go back to grade school when you learn division, right? Like if I asked you to take 15 and divide that by 4, right? You would go, put your 15 in here, divide by 4, and then what's the process? You just ask yourself, what do I multiply 4 by to get 15, right? So you say, okay, what number times 4 gives me 15, but I can't go over, right? So you say, oh, 3, right? And then you go, oh, 3 times 4 is 12, right? You put that under here, and then what do? This important step. Subtract it, right? So you subtract that, and then 15 minus 12, you have a 3. And then you ask yourself again, how many times does 4 go into 3? And in this case, it does not, right? It doesn't. So what we would normally, and this is like way back in grade school, we put R3, right? Remainder of 3. But then after that, they tell you, oh, don't do remainder of 3. Instead, write 3 and 3/4. Remember seeing that? So it's 3, and then you take that 3 and you divide the remainder and you divide it by the 4, and that gives you this. And everyone in here should know that that really means 3 plus 3/4. This notation right here, do y'all know what this is called right here? This notation? Mixed number, good. That's called a mixed number. And we use it a lot in grade school, and then we kind of stop using it. Once we get into like college, we stop using it. And there's a reason why. The reason we stop using it is because, well, there's a couple of reasons, but one reason is that people don't really understand what this is. Like 3 3/4. It really means take 3 and add 3/4. Okay, so it's just a weird notation because you're taught like that this should maybe be multiplication, right? Like if there's nothing in between them, it's implied multiplication, so it's confusing. So we kind of like ditch this notation after a while. So it's more important that you understand that 3 remainder 3 here really means 3 plus 3/4. Okay, that's long division. That's how we do long division of numbers. So when we go to do long division of polynomials, right? Here are 2 polynomials, we're going to divide them. We're going to do the same procedure with a couple of little exceptions. Inside the division box, I'm going to put the numerator. Okay, this is going to go in the division box. I must put it in descending order. And that means the highest power of x down. So if for some reason it's mixed up in a different order, we always want to make sure it's in descending order. So I'm going to put x cubed first, then minus 4x squared. And then critical step, do y'all see that I'm missing an x term? Like there is no x's here. So what I'm going to put here is plus 0x and then minus 5. Now, the reason why I want to put that 0x there is because when we do long division, we have to line things up. And if you don't have a gap or space there for that x, for any x terms, you can start to run into some trouble. So that will just help us from making a mistake. Now, on the outside, we put the divisor, the x minus 3, and again, we put it in descending order. And now we play the same game that we played, you know, when we were saying, hey, what do I multiply 4 by to get 15? I'm going to do that. But instead of looking at the whole thing and saying, what do I multiply all of this by to get this? It actually becomes a simpler task if we just look at the first term, x, and ask ourselves, what would I need to multiply x by to create an x cubed? So to turn x to x cubed, you have to multiply by x squared, right? So I'm going to multiply by x squared. And the x squared, I'm going to put it up here, just like we put this 3 up here. Where you put it doesn't matter. I've heard certain people teach it and they're like, put it right above this x squared. It doesn't matter. I'm going to put it above the x squared, but you can put it anywhere. Okay. So there's x squared. And then just like we did here, to get this 12, we multiply 3 times 4, right? So I'm going to do the same thing here. I'm going to take x squared. I'm going to multiply it times this entire thing. So think about what that means. On the side, we're multiplying x squared times x minus 3, right? That's the multiplication, which means it would have to distribute to each. So we should get x cubed minus 3x squared, right? That's what we should get when we multiply this x squared by this. So I'm going to write that down below. And notice I'm going to line things up. I have x cubed here. This is minus 3x squared. So I put that right there. And then I'm done, right? I've done my first multiplication. So I'm going to come through just like we did with the 12 here. We're going to subtract it. So we subtract. Now, when we subtract, really it has the effect of changing the signs of these. So the first one becomes a minus x cubed. And the second one that was a minus now becomes a plus. It's all good? Y'all kind of give me the feeling here, at least y'all that are here in class, that you've done this before. You've seen this. Okay. I'm going to go through it like you haven't, but let's just crank this out. All right. So we add down now. The x cubes go away. That's supposed to happen. And then the rest of it, we just have to bring everything down. So how many x squareds will we have? -1, right? We have -4 of them. Add 3 of them. We should have negative x squared. We have no x's, right? I'm not even going to put anything. We have nothing here. And then here we have -5, and we're not doing anything to it, so -5. Okay, there we go.
So we don't bring down the x from the 0?
If you want to bring down the 0x, you can. Totally up to you. It's not necessary. What do you do once we get here? Since you all said you've done this before, what do we do now? Multiply by -x. And the idea here is that you're trying to figure out what you multiply x by to get -x squared. So you multiply by negative x. So we're kind of like playing the game over again. So we multiply by negative x on top. And if you need to, you don't have to do this, but you can go to the side here and see what that would be. Negative x times x minus 3. So you're multiplying this negative x times this thing. Gives you negative x squared, and then plus 3x. Be careful there, because negative and negative is positive. And let's put that underneath here. We'll have negative x squared, and then here plus 3x. I think on that step, you can see how important it is to have a column here for x's. If you did not have a column for x's, then like where would you put this? You wouldn't want to put it underneath the 5. So this gives us a space for it. Now we come through and we subtract. So we change the signs. That becomes a plus. And then this plus now becomes a minus, doesn't it? And we add down again, right? The x squareds go away, gone. Here, we're going to get negative 3x. And then minus 5 comes down again. And we keep playing this game until we can't anymore. So I think we can keep going, right? What do I multiply x by to get negative 3x? Negative 3. I guess they call it long division because it takes a while, I guess. Negative 3 multiplied times x minus 3, distribute negative 3x plus 9. That's what goes under there. So negative 3x plus 9. And then we come through and change it again, subtract. So it changes the minus to a plus there. It changes the plus to a minus. And when you add down, what do you get? Negative 14. And this is where we're going to stop, because there's no way to turn x into negative 14 unless we use a fraction. Because we could multiply by negative 14 over x. I mean, yeah, right, that would work. Negative 14 over x. But we're not going to. So with division, long division, you stop when you have to start resorting to fractions. So I stop here. This is my remainder. So I could say, okay, remainder negative 14, right? That's like old school, elementary school idea here. But we're not going to do that. Instead, what we're going to do is we're going to take this and say that the answer is x squared minus x minus 3 plus the remainder, which is negative 14, over the divisor, which was x minus 3. And that is the long division, okay? What we are saying, okay, and this is actually really important. What we are saying is that if you take this expression, okay, take this expression that we started with right here. If you plug a value of x into this right now, okay, just if you pick an x, like 5, plug 5 in. If you plug 5 in here, you will get the same answer as plugging 5 into this. Okay, these are equivalent. Okay, this equals this. Now, what does this have to do with the theorem? What does that theorem say? Oops, wrong one. The theorem says, suppose f is a polynomial function, and then we divide it by x minus c. Then, this is the important part, the remainder is f of c. The remainder is f of c. What the hell does that mean? Well, what was our remainder here? Negative 14, okay? Our remainder in this problem, where was it? Right here. This right here, this was our remainder. What did we divide by? What did we divide by to start this off? X minus 3, right? We divided by x minus 3. According to the theorem, if I divide by x minus c, then the remainder is what the function's value is at c. So for us, what is c? If we divide it by x minus 3, what for us is c? That means c is 3. And according to the theorem, if I take that value of c and plug it into the function, what should my answer be? Negative 14. Now, what we would have to do is check it, right? We could check to see if that was true. we could take negative 14 and plug it into the original function. I'm going to go ahead and do that. Let's take the original function here. Oops, wrong. Oh, there we go. Take the original function. And I'm going to plug into it 3, just to show it worked. So if I take 3 and I cube it, and I subtract 4 times 3 and I square it, minus 5, then we get 27, take away, this is 9 times 4, right? 9 times 4 is 36. What's going on here? Yeah, and then minus 5. Okay, and then these two together give me negative 9. I take 5 away and I get negative 14. The theorem is saying that that is not a coincidence. The theorem is saying that will always happen. All right. So if you divide by x minus a number, that's the same as plugging that number into the function. Well, why would you ever want to do that though? Because didn't this like take me about 5 seconds to do? And that took us about 10 minutes to do? Like, why the hell would you ever want to do this to figure out what 3 being plugged into the function is, right? It doesn't seem like it would be worth our energy. Do you agree? I agree with that. I mean, it's just like, why, right? Well, just you gotta be patient with us, all right? There's a reason. So the next part of this problem is that we want to do the same thing with x plus 2. Okay, I'm gonna do the same thing with x plus 2. Now, if I use x plus 2 and use this theorem, what is c? Well, careful, because in the theorem it says x minus c, right? So if we have x plus 2, what's c for us here? Negative 2, all right? Just like here, it was x minus 3, so c was 3. Here, x plus 2 means that c would be negative 2. So I'm going to do the long division. It's going to suck. I'm going to go a little faster. But whatever happens, right, should be the same thing that happens if I plug negative 2 in here. Yes.
What was the answer so far? Was it negative 14 or was it x squared minus x minus 3?
Good question. Good question. So what's being asked is what's the answer to the question here? It says here to do what? Find the remainder. So the answer would have been negative 14. Okay, because all they wanted was the remainder. If they said, take this polynomial, divide it by this, and tell me what the answer is, then the answer would have been the x squared, blah, 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 all that stuff with the negative 14 over x minus 3 on the outside. All right, so here we go. We're going to divide it by x plus 2. X plus 2. I'm just going to copy this here. Okay, so here we go. Part B. I'm going to divide by x plus 2 instead. And I'm going to go faster. So here in my division box, I've got my x cubed minus 4x squared plus no x's minus 5 x plus 2. Okay, here we go. Got it written down. It's 123. It's taking me about a minute maybe to copy it down. Let's see how long it takes us to do this. I'm going to go pretty quick.
Professor, I'm so sorry.
Yes. Uh-huh.
Why is it x plus 2 and not minus 2?
Because the original question asks us to do x plus 2.
Okay,
But
we
what I'm
don't.
saying is in the theorem, they say if you divide by x minus a number, then that's the same as taking that c value and plugging it in to the polynomial. So we need to be able to see that x minus 2 is the same as x plus 2 is the same as x minus negative 2. And therefore
Okay.
c is negative 2. Make sense?
Okay, yes, sir.
That will come up at the end when I check our answer. Okay, here we go. To get x to x cubed, I need x squared. I multiply x squared times x, I get x cubed. Multiply x squared times 2, I get 2x squared. Come through and subtract. Minus, minus. I subtract down, I get negative 6x squared. I'll go ahead and bring that 0x down, minus 5. Those canceled. Now to get x to turn into 6x squared, I need a plus 6x. 6x times x gives me 6x squared. 6x times positive 2 gives me 12x. Come through and subtract. These go away. nothing, take away 12x is negative 12x minus 5. And then to turn x into negative 12x, I need a negative 12 up there. Multiply negative 12 times x, I get negative 12x. And then negative 12 times 2 gives me negative 24. Change the signs one more time. Add down, and what do we got there? 19? Okay, 19. That's our remainder. So that would be the answer to the question, like, what's the remainder?
Can you make sure the 6x squared there is negative?
Which one? Oh, did I mess this up? Why didn't y'all say something? Right here I did, didn't I? See, this is the danger of going too fast. Right? This should have been minus, minus, minus. Oh, well, I screwed it up. I'm glad someone's paying attention. Back it up. All right, let me slow down. Negative 4x squared, take away 2x squared, we get negative 6x squared. Of course, that's going to change the whole answer, right? Like, okay, I got to get that out of there. All right, this is that. I can bring down the 0x minus 5. We good on that step? Yes. Now I need to multiply by what? Negative 6x. Now, so I was going to check my answer by plugging negative 2 into the function. We would have seen we had a problem, right? Okay, so here I multiply here to here, I get negative 6x squared. Negative 6 times positive 2 is negative 12x. Come through, change the signs. Add down, these go away. Here I have positive 12x minus 5. Then to turn x into 12x, I have to multiply by 12. 12 times x is 12x, and 12 times 2 is 24. Change the signs one last time. Negative 29. That should be the answer. Now, I'm going to check it by seeing what would happen if I had taken negative 2 and plugged it into the function. Now, the original function was just the top. So I take negative 2 and I cube it. I subtract from that 4 times negative 2 squared, then subtract 5. Negative 2 cubed is 8. Let's see, negative 8. And then negative 2 squared is 4, then times negative 4 is negative 16. And then take away 5 again. And there we should get, yes, negative 29. There we go. So they check, right? But again, why go through all this where you can make mistakes? Obviously, you can make mistakes, right? So it does not seem like worth it to us, right? And I would say that it probably isn't worth it to us to do this if we're trying to evaluate the function. Unless we have a faster way of doing this, right? Unless there's a faster way, something even faster than this. And that's where synthetic division comes in, all right? So I'm going to do the same problem, the same two problems, A and B, using synthetic division. That's just a different method. Long division, synthetic are just two different methods. So same problem. And we did this last class, but I'm going to kind of run through it again. The way we do synthetic this time is we take the original polynomial right here and we write an upside down division box. We put just the coefficients of this polynomial in descending order. So 1, -4. This time you have to have a 0 and then -5. So this is the number in front of x cubed. This is the number in front of x squared. This is the number in front of x, which there is no x here. This is the number in front, well, the number that's by itself, right? You don't need to write this, but this is kind of telling you how many x squareds you have. Sorry, x cubes you have, how many x squareds you have, how many x's you have, and then how many of a constant you have. Now, the number on the outside here is C, is the C from that theorem. So what was C for us for part A? +3. Okay, so +3 is going to go out here. And then what we do is we take the first number, we drop it straight down. Okay, so that number just drops straight down. Then we go 3 times 1, which is 3. Put it underneath here. Add down, -1. 3 times -3 gives us -3. Add down again, -3. Multiply 3 times -3, put it here, we get -9. Add down one last time, we get -14. And that was the same answer, right? -14. So this number here is our remainder. But not only is that number our remainder, right? This is also f of 3. That's what happens if I plug 3 into the original function, right? If I plug 3 into the original function, I get -14. So to do part B, the only difference for part B, do the same synthetic division here. 1, -4, 0, -5. The number we use on the outside this time for B is -2. It's the opposite of what I see here. Bring the 1 down, -2. Underneath here, add down -6. Multiply through, you get 12. Add down, get 12. -24. And you get a remainder of -29. So I just did that pretty quickly. And, you know, as you do synthetic more and more, you get faster and faster with it. And it gets to the point where this is actually faster than the other way, because all you're doing is multiplication and addition, subtraction. If you plug numbers into these polynomials, you're squaring, cubing, fourth power. There's a lot of room for mistakes there. Any questions? Yes. Yeah, so yes and no. The question is, these are both like completely legitimate methods, right? Like they don't mess up. Yes, they are both equivalent. The catch is this. We can only, well, they are both equivalent if we're dividing by a linear expression. So you know how here we said, let's divide by x minus 3. Let's divide by x plus 2. If we, these are linear expressions. X minus 3 is linear because it's x to the first power. X plus 2 is linear because it's x to the first power. If I changed one of these to, let's say, x squared minus 3 or x squared plus 2, synthetic is out the door. There is no synthetic division whenever the divisor's nonlinear. Okay, so synthetic is great as long as you're dividing by linear stuff. As soon as the linear goes away, well, then we have to go to long division. That's why you have to know them both, because in Cal 2, we're dividing by stuff that's not linear. And so you have to have a method. If it's linear, synthetic all the way. That's the way you want to go because it's fast. Does that answer your question? Okay. All right. So for us here, we're going to be focused on synthetic because everything we're going to be doing is going to be linear. Yes. Yeah, if the question was just find the remainder, and I gave you these two, you could just plug 3 in, plug -2 in, you get the same answer. But I'm never going to ask you this question on a test, right? This is leading us up to something, right? We're trying to lead to something. What we're basically trying to do is come up with a new way of factoring, and this is going to lead us there, okay? So let's look at the next theorem. This is the big important theorem for today, really. Suppose f is a polynomial function. Then x minus c is a factor of the function if and only if f of c equals 0. What is that saying? Let me take you back to this. If I ask you to do 15 divided by 4, right? Old school way, you're going to go 15, 4, it goes in there 3 times, that's 12, you subtract, you get 3 and you get a remainder of 3, right? That's what happens when we do old school. Now, if I do 15 divided by, let's say 3, 15 divided by 3, well, that goes in, doesn't it? Nice. 5, 15, subtract, what's your remainder? Remainder is 0. What is that telling you? It's telling you that because when you took 15 and divided it by 3, you got the answer of 5. It's really telling you that 15 can be rewritten as 3 times 5. This number 15 can be rewritten as this thing that you divided by times the number that you got here. So essentially, I have taken the number 15 and I have factored it into 2 factors, right? But that only works if the remainder is 0. If the remainder is something other than 0, like up here, like this, then this is saying that 15 is equal to, well, not 3 times 4, it's 4 times, what? 4 times 3 plus the remainder over the divided plus 3/4. Yeah, that's true, okay? This is true, but we haven't truly factored it into 2 numbers. We factored into a number and some fraction. We want 2 whole numbers. So the remainder being 0 basically guarantees that we've factored. Okay? So let me go back to this problem right here. The 2 that we did with synthetic, and I'm just going to copy this. And I'm going to put this here. I'm going to show you how that second theorem works, or what it's saying for these 2 problems. The fact that I did not get 0 here, right? The fact that I did not get 0, this is not 0, means when we take the original problem, let me go back to where the original problem is, right here. Copy. So the fact that this is not 0 means that when we take this expression, I know that this original top right here does not factor to be x minus 3 times something. This does not happen. I cannot break down x cubed minus 4x squared minus 5. I cannot factor, it cannot be broken down to be x minus 3 times something. If this had been a 0, then yes, that would be true. But because it's not, that's not going to happen. This one is saying, the second one, again, because that's not 0, says that if I try and take x cubed minus 4x squared minus 5, that will not be equal to here x plus 2, which is the thing that I divided by, times something. That's impossible. So x minus 3 is not a factor, and x plus 2 is not a factor of this, because my remainder is not 0. Now, what if it is, right? That's the thing we're interested in. What if it is 0? So let's look at that theorem again. Go back to it. Here we go. This is a different problem, a different polynomial, and they want to know whether or not these two things are factors of this. That's what they want to know, right? Use the factor theorem to determine whether this function has one of these as a factor. So here's what I'm going to do for part A. Can someone tell me what I'm about to do? Synthetic division, okay. Inside the division box, I'm going to have what? What are my numbers? 2, -1, 2, -3. And outside the division, careful, 1. Okay, so for part A, x minus 1, I put a 1 out here. Now, what I'm hoping for is a 0 as a remainder. 2 comes down, 2, 1, 1, 3, 3, 0. Okay, I did that quickly. 2 came down, 1 times 2 is 2, add down, get 1, 1 times 1 is 1, put it here, add down 3, 1 times 3 is 3, put it here, add down 0. So is x minus 1 a factor? Yes, x minus 1 is a factor. So because of this, yes, x minus 1 is a factor. That answers the question, okay? That answers the question. That's all they wanted to know. But I showed you this last class that there's a lot more information in this that we can use. This right here tells us, well, what we just concluded, that x minus 1 is a factor, right? The other part, though, the other part that's left will always be these three, or whatever numbers are left here. These three numbers actually mean something. And what they are the coefficients of the other part, the other factor, I should say. So what is this going to be? I'm going to have a 2 here, and then I'm going to have a 1 here, and I'm going to have a 3 here. Now, what goes next to the 2? So it's going to be x to some power. What? X squared. Now, the reason we know it's x squared is because the original polynomial started out with x cubed. Whatever x goes here is always 1 less power than what you started with. Okay, so this is going to be a 2x squared plus a 1 what? X, and then a plus 3. So here's what we're saying. We have actually taken this thing right here, and we have actually factored it. We've taken this ugly polynomial to begin with. If I had walked in today and I said, hey, everyone, try and factor this, you would not be able to do it. If you tried grouping, it wouldn't work. Okay, grouping would fail here. But because I asked you to try this, well, we got a remainder of 0. Now we know that this is a factor, and just working off the synthetic division table, I can actually come up with the rest of it. Here's the rest of it right here. So I know that this is going to be these two multiplied together. You can check your work if you check it if you want. Expand this out, you should get this. Okay, so we have factored. Now let's try the other one, part B. So for part B, I will have the same table here, won't I? Oops. For part B, won't I have the same thing? Except something different on the outside, right? So 2, -1, 2, -3. On the outside of this one, I'm putting the opposite of this number, so -2. And now I just start cranking it out. 2, -4, that's -5, 2, that's 10, that's not looking good here. 12, -24. This is not going to be 0, right? I got -27. Check it. 2, -4, -5, 10, 12. Yeah. No go. So it's not a factor, right? It's not a factor. So in everything I've done up to this point, I've given you the polynomial and I've asked you to look at the little linear thing and check, right? Now comes the big part. What if you're not given the little linear thing to check? How do you come up with the kind of guesses as to what works and what doesn't work? And that's the last major note of today before we get into the 4 problems I want to try and graph. And this is, we did talk about this last time. This is what's called the rational zeros theorem, or I referred to this in class last time as the rational zero test. Either way, however you want to do it. So what you do is you look at a general polynomial, and this is really ugly to look at. Just imagine that this is a polynomial that starts with your highest power of x. There's some number in front of it. And then at the very end of your polynomial, there's some number by itself. What you're going to do is you're going to take all the factors of both of those numbers, and you're going to create this list. Okay, and we did that last class. We're going to do it again. I don't want to read through the note because the note's confusing. It's easier if you just do it and, like do an example, and then you're like, okay. So let's do this one. The questions here are for us to find the zeros of this polynomial function. What do they mean, find the zeros? The x-intercepts, right? They want to know what number we plug into the function to get 0, right? What number do we plug into the function to get 0? Well, First of all, before I even do anything, does anyone know what the maximum number of answers we can have is? 3. Why? The highest power. So there is a theorem, which I did not put up here, that if you are looking at a polynomial, the maximum number of zeros you can have, the maximum is the highest power of x that you see. So the max we could have here is 3. It is possible to have 2. It is possible to have 1. It is possible to have none, but you can't have 4 or 5 or 6 or 7. 3 is the max, all right? So if there are any answers, the most we should get here are 3. So let's start running through the procedure here. First thing I'm going to do is I'm going to look at the number in the back, -6. And I don't even care that it's -6, okay? I don't even care. We call that number P. And I will put -6. But now what I want to do is write all the factors. What are all the factors of -6? So here's how I do it. I start with 1. Right? I can multiply 1 and 6 together. And I can do it in different ways. I can do 1 and -6. I can do -1 and +6, right? I can do all these variations. So the way I write it is this. I do ±1. And then back here at the backside, I put ±6. So if I do 1 and -6, or if I do -1 and +6, these are actually 4 factors, aren't there? There's 4 numbers there. Then I continue my list. Now I move up and I try and think, is 2 a factor? Well, 2 and 3, right? So I put ±2 here. And then on the back side, I put ±3. And what I do is I keep building this list until I get to this middle point where I meet, which I've actually gotten to that point already. Do y'all see that? Because the next number after 2 for me to try would be 3, but we've already done 3. 3's in our list. So I can stop here. Does that make sense? Now, the next number I'm going to look at is the number in front of the highest power of x, which is 2. And that's q. We call that q. And it's 2. And now I write all the factors of 2. And I do that again. I can do 1 and 2. Right? Positive and -1, positive and -2, put those together. And then I move to the next number, which is 2, but that's already in my list, so I'm done. Those are the only numbers, the only way you can get to multiplying 2 numbers together that aren't fractions. They have to be nice whole numbers. All right, once you have P and Q, what you do is you make a final list. And the way I do it is I say, okay, take this list here and divide each of them one at a time by this first number here. So if I take ±1 divided by ±1, I'm going to get ±1. If I do ±2 divided by ±1, I get ±2. If I do ±3 divided by ±1, I get ±3. And ±6 over ±1, I get ±6. So basically, that's just a repeat of the first list, right? And then I do the same thing, this list again, but now on top of this. So what's ±1 over ±2? A half, ±1/2. And then ±2 over ±2, ±1, which I already have, right? I've already got it, so I don't need to write it again. ±3 over ±2. 3 halves. ±6 over ±2.
3.
±3, which I already have. So that's it. That's my final list. So the way this theorem works, is, and then let me put the theorem back up here so you can see it. If f is a polynomial of degree 1 or higher of this form, okay, where, you know, blah, 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 we got this P, Q, right? Then this test only works if our function has rational zeros. This will only work if our function has rational zeros. Rational means fractions. So you know how when you look at x-intercepts, you know, you could have like x equals 2, that's an x-intercept, or x equals -5. If we have answers that are fractions, like 2 is a fraction, right? -5 is a fraction. +1/2, 3/4, something like that, then this will work. If one of our x-intercepts is irrational, this test fails. So like if one of your x-intercepts is the square root of 2, this test won't find it. I'll show you after this. I'll show you how it fails, all right? But as long as the answer is a fraction, this will work. So this is our list, okay? And now what we need to do is we need to check every single one of these until we get a 0 out of synthetic division. So where do we start, right? Like, let's start by doing the synthetic division box. Let's put 2, 11, -7, -6. Where do y'all want to start? I'd prefer to not use a fraction to start. Let me see, make sure I got this right. Yeah. I always like to start at 1. I mean, we may as well, right? Let's start at 1. So I'm going to go 1 here and then just start cranking this out. 2, 13, 13. Ooh, what's that? Negatives. Oh, sorry, +6. Is that it? Did I get it on the first try? Two times 1 is 2. Add down 13. 13 times 1 is 13. Add those together. I get 6. 1 times 6 is 6. Hey, we got lucky, right? First try. First try. So now what this tells me, okay, what this tells me is that this tells me right now that x equals 1 right there is a 0 of the function. If I plug 1 in, right? If I plug 1 into this function, I should get 0. Agreed? So I have found 1. There might be more. There might be more. So for me to continue, I have 2 options. I can continue using synthetic division, okay, to try and find the others. Or I can use the fact that I know that this factors my original polynomial to be x minus 1, 2x squared plus 13x plus 6, and then ask myself, can I factor this? Can that factor? Do you understand what I'm saying? Can this factor? Well, does it? Believe it. Believe it may. Believe it may. It does, but let's act like we didn't know how it factors. Okay, let's just pretend we don't know, because I know there are probably some of you that would struggle with that. So what I'm going to do is I'm almost going to like reset everything in my mind again. And I'm going to say, hey, I'm trying to factor this now, right? Oops. I'm trying to factor this. So I'm going to set up a new synthetic division over here. I'm going to use the numbers 2, 13, and 6. And then I'm going to try the synthetic again, right? But I can use the same list. That's the great news, is that I don't have to make a new list. I can just continue with this list. So what number should I try? Should I try 1? I mean, 1 worked, right? So should I try 1 again? You need to. It could work twice, okay? It could work twice. So when you're doing this, even though it might work once, if you're trying to break something down, repeat it, try it again. If it doesn't work, that's okay. We'll throw it out. We won't worry about it. It's not going to, but here 2, 15, 15, and then that right there is not 0. So that didn't work, right? So I'm going to keep going. I'm going to try another one now. 2, 13, 6. How about -1? Let's try -1. So 2 comes out, -2. This isn't going to be enough, is it? -11, no go, right? No 0 there. So I just have to keep going through this list. I've taken care of the 1s. Now let's move to the 2s. Any questions on what I'm doing here? Other than, is there a faster way? I'm going to go to 2, right? You know what? I'm going to go to -2. Why am I going to skip the 2? Why am I skipping 2? These are all positive numbers, right? So if I start multiplying things with positives and they're all positive, I'm never going to get anything to subtract. So I'm going to go to -2. I think it'll be faster or more hopeful. 2 here, -4. What is that? 9? That didn't work. Nothing. No go there. Has anyone worked ahead of me here? You got this? 1/2 works. 6 also? Okay, so I'm going to go. So we would have had to, we could have thrown out, I think, safely thrown out the positives here. We already tried -2. So next one would be 3. I'm going to go ahead and do 3 and 6. I'm going to do them quickly. So here's 3. Sorry, -3. So 2 comes down, -6. Okay. This adds up to be what? 7, and then multiply -21. That doesn't work. -6. 2, 13, 6. So 2 comes down, -12. Oh, there it is. 1 and -6. 0. Yay. Okay, we got it. So I'm out of room here. I'm going to copy this to the next page. So here's where we were, right? We were here. We had done the synthetic division. The 1 worked. We were all happy. Then we got to this, said, shit, I don't know how to factor that. And then we started doing it more. And then we finally got to this one, which worked. So what does that tell me? That tells me that X, what is a factor? X plus 6 is a factor. And the remaining factor is these 2 numbers, right? And it'll be 2 what? 2x plus 1. And the reason it's an x is because 2x, 2, 13, and 6 came from this, which was quadratic. So this should be linear. And so this will replace the part in blue. And we have our final factored form of the polynomial. X minus 1 times x plus 6 times 2x plus 1. Now it's completely factored, right? That's the factored form. And to answer the question, right, we need the zeros of this, right? What are the 3 zeros? We just set each of these to 0, right? So 1, -6, and then -1/2 if we set each of these to 0. All right, what do y'all think? Y'all ready for some more challenging problems? This was just to get the idea going. Here we go. There we go. I want you to sketch this. All right, so I'm going to give you some time to work on it. You can work together, you can work alone. I don't care how you do it. But I want you to follow the steps that we did last class. Do you want the steps up here or no? You okay without them? End behavior, x-intercepts, multiplicity, bounce cross, right? And draw it. The issue for you obviously is going to be finding the x-intercepts, right? Setting this thing equal to 0, which means you're going to have to factor it, which means you're going to have to break out the list and start cranking stuff out and see how it goes. All right. Okay, I'll give you, let's go for about 10 minutes, see how far you get with it. I'm just going to step away for a second and mute my microphone. Yeah, so this starts to become like how fast can you get with this? Because speed, if you don't become quick with it, it can really start to eat up a lot of time if you're taking an exam, right? If anyone has any questions, just let me know. I recommend on your list that you start with the small numbers. I like to tell my students that on a test, I would always make it where something's going to work within the first like 6 tries. You know, I'm not going to make a test where you got to go like 13 numbers out to get to it. Do 1, then -1, then 2, then -2, and is it nasty or what? How are y'all doing at home? You making any progress?
I'm sorry, Professor, you cut out. What was that?
I was asking if y'all are making any progress at home.
Yes, definitely.
Okay. Well, y'all are working it. I'm going to start working it, and then we can talk about it. And then 118 times. Oh, I forgot one. It's been almost 10 minutes. Are y'all ready to talk or you want me to give you more time? Does anyone have it? A little more time? Okay. Yeah. Okay. All right, I think we should talk about this. We've got a polynomial that has a degree of 6, which is even. We have a leading coefficient. The number in front is 1, that's positive. So off of our table from last class, both sides go up. The x-intercepts, you set the polynomial equal to 0. Hopefully you looked for GCF first. That's always the first thing we want to look for. So there's an x squared in all of these. I pull that out. So I right off the bat already know one of my x-intercepts. I can set this equal to 0. I get a solution of 0. And I went ahead and already put here that it's going to bounce here. And I know it's going to bounce because that x, where the 0 came from, is a squared factor. And anytime the power is even, you bounce. If it's odd, you cross, right? So then I'm left with this big, nasty, ugly thing in here, a 4th degree polynomial. So I'm going to do the rational 0 test on it because I have no idea how to factor it any other way. Luckily for me, the number in front is a 1. And when it's a 1, your list is always just this list for the last number. So I just started to write down all the factors of 90, which was a super long list. 1 and 90, 2 and 45, 3 and 30, 5 and 18, 6 and 15, 9 and 10. Did I miss any? I think I've got them all. And now the tedious step of the synthetic, no long division. I don't want to do long division. Synthetic division. So did 1 work or no? No? Okay, so I'm going to do 1. And then I'll ask you for what works. Okay, so 1, I try that, 1 comes down, 1, that's -8. It's -8. That gives me 9. 9 here, that's 42, 42, and that is not a remainder of 0. So that didn't work. So what did work? -2 is the first one that worked. So on your exam, like I said, what I want you to do is, I promise you it'll happen, like it'll work within the first 6 tries, but always start with the smallest numbers, do plus or minus, plus or minus, plus or minus, and don't do fractions until the end, okay? So, all right, so you said -2 works? Let's see here. So 1, okay, -2 here, that's -11. That's 22, that's 39. Negative, what is that? 78? What is that? -45. And then you multiplied 90, great, I get a remainder of 0. Okay. So right now, just as a side step here, is what I want to be thinking to myself is that right now at this point, I know it factors to be x plus 2. That's coming from this piece right here. And then this is the remaining piece. Now, what power would I have? This 1 would be in front of x to what power? Third power, because the thing I'm trying to break down was at the 4th power. Don't be looking at the 6. You already pulled that x squared out. You're looking at the 4th power here. So this should be 1x cubed minus 11x squared plus 39x minus 45. The reason I think it's useful for you to actually write this down is because what if this goes by grouping, right? Like this might go by grouping and then you don't necessarily need all this, but it doesn't. So I have to keep going. So I'm going to continue now, synthetic division. I'm going to do 1, -11, 39, -45. I know some of you learned that you can just continue working off of this. I know some of you all have been taught that you can just continue working right there and just like do more synthetic. That's fine if you want to do that. I always separate it. So if I were doing this again, like if this were just me and I got to -2 and it worked, the next number I would try would be -2 again. Okay, now don't tell me, I'm going to be surprised. I'm going to try -2 again. 1, -2, -13, 26. That's not going to work, is it? That doesn't work. Okay. So because that doesn't work, now you move on. Any questions? The next number I would try would be 3 and then -3, right? Then I would go to 5, -5, 6, negative. So someone have the next one that worked? +3 works? Okay. So 3, so what I get here, I get 1, 3, that's -8, -24, this right? 5, 15, and then 15 times 3 is 45. And yay, we have 0 there, okay? Now, what does that tell me? Watch. That tells me this comes down, x plus 2. But this here now breaks down using that 3, x minus 3. And then the remaining piece is this. And this should be starting with x squared because we were trying to break down something that had x cubed in it. So this becomes x squared minus 18x plus 15. Okay. And then we can try and see if that factors. Does that factor? Should. Oh, wait, yeah, I wrote -18. Oops. I was like, that doesn't look like that factors. -8, I'm sorry. That -8 came from here, right here. Don't know where I grabbed 18 from. Yeah, that should factor. Now, you could do synthetic again, all right? But you hopefully can get to a point where you get to something that you're comfortable with, like a quadratic, and hopefully it factors. So x minus 5x minus 3. Hey, so 3 would have worked again. I know that right now. Because I have 2x minus 3s, I know that 3 would have worked again on this one. Okay, so I'm there. I have got it all broken down. I can actually rewrite this. Let me write it like this. Doesn't matter which order these are written in, by the way. Because I have x minus 3 twice, it's x minus 3 squared. All right, going back up here. Okay, here's where we were, right? Right here. Put that right here. That's where we were. And now what I can say is this is finally factored out to be x plus 2, x minus 5, x plus, minus 3 squared equals 0, right? That's the final factored form. Now look, we have to actually take a step back and kind of appreciate this, you know? I mean, asking you to solve this equation, that's a pretty crazy thing to be asking you to do, right? I mean, if you don't know any of these techniques with the synthetic division and all that, trying to solve this 6th degree polynomial equation, generally speaking, is very difficult, right? We actually have a method. And theoretically, this would work for any degree. You know, if your polynomial was degree 30, we have a way, which is nice. I'm not telling you it would be fun, but okay. So this, we set each of these equal to 0. We already did this one. X was 0, and we're going to bounce because the power up there was a 2. What about the next one? X-intercept at what? -2. What are we going to do there? Cross. We're going to cross because the power on that factor is a 1. The next x-intercept is at 5. Cross again, right? Because the power there is a 1. And then the last one, set that to 0, you get x is 3. And we're going to bounce here because the power there is a 2. Okay, so just remember that we're basing the crossing and the bouncing off the powers, not off the number, right? So we should be ready to graph this. Any questions at home?
Everything looks pretty good so far, Professor.
Okay, thank you. So here I go. Time to draw this thing. I just want a rough sketch of what's happening here. So start with my x-intercepts, 0. I've got one at 3. Just make sure these are in order, that's all. 5, doesn't have to be perfect. And we have one more, -2. We only have 4 x-intercepts, right? It was a degree 6 polynomial. We have 4 x-intercepts. We know with a degree 6 polynomial, we can have up to 6. We have 3 though. I mean, sorry, we have 4. All right, we know the left side goes up. So I know the left side went up and the right side went up. And then I know what's going to happen at each one of these. So when I get to -2, I'm going to cross through. What happens when I get to 0? Bounce. So I'm going to bounce off at 0. When I get to 3, what am I going to do? Bounce again. And then when I get to 5, cross through and connect it. Just make sure that your graph looks relatively smooth and curved. That's it. That right there is what I'm looking for, you know, when we take a test on this next week. I want to see just an ugly sketch. All right, we don't care how far this goes down. Let's go look at the computer. I already have this ready to go.
Sir, I have a question.
Yes,
Can you go over just like the endpoints where the direction? Just
This
kind of
here?
information.
the up and down, the up on both sides.
Yes.
Yeah, that came from the first thing we do when we look at a polynomial function is we look at the degree and we look at the number in front, the leading coefficient. And we use something from last class. Where is it? Right here. We use this leading coefficient test. That if the degree is even and the leading coefficient is positive, we have up on both sides. And then if the degree was even and the leading coefficient was negative, then we know both sides go down. And then this is if the degree is odd, leading coefficient positive, and then odd, leading coefficient negative. Do you understand what I'm saying?
Yeah, I was just confusing the leading coefficient if it was even and odd, not
No,
positive.
you always check for leading coefficient, you're checking positive and negative. For the degree, you're checking even and odd.
All right, I got it.
Yeah,
Thank you.
so on ours, our degree is 6, that's even. The leading coefficient is 1, that's positive. You good?
Yeah, I got it. Thank you.
Uh-huh. Okay, let me show you the graph of this. Where is she? Here's the graph according to the computer. And when you look at this graph, I mean, there's really not, it's such a crazy polynomial that when you graph it, it's kind of hard to see what's happening. You have to really adjust your window. You'd really have to adjust your window to see this. Let me see. Hey, not bad. I adjusted the window to kind of fit things in and make it look better. Oh, that looks a lot like ours, doesn't it? Didn't take the computer quite as long, but okay. Here's the next one. So let me do this. I think I'm going to let that one be a homework problem. I want to do one that has, yeah, let's do this one. So I can let you work it yourself or I can work it with you. It's up to y'all. What do y'all want to do? Do y'all care? I think this is what I'm going to do. I'll put that back up there. I'm going to grab these. I want to put them all on one page. I think I'm just going to make this your homework assignment. Let's see. There we go. I'm going to make these 3 problems your homework. Go ahead and take a few minutes or a minute or so to just jot all those down. I think I want to use the remaining time to show you just an example of how the rational zero test can fail to work and how we would go about doing something where it failed. All right. So this is homework for next time. We'll call it problem 1, 2, 3. That way, if we need to reference it later, we'll know what we're talking about. The only kind of hint I have for you on this, I mean, you pretty much have the method. There's nothing new. Just remember that when you're using when you're doing the synthetic division, if one of them works, like use it again, okay? Because it might work a second time. And if you don't do that, you might catch yourself in trouble there. Not trouble, but you'll just be like way down the list before anything works. All right, y'all got that? A little more? Got it? Okay. I'll put it back up at the end of class if you need it. All right, so let's take a look at something like this. All right, so we know right away this goes up and up, right? Up and up. Even degree leading coefficients positive. If I go to find the x-intercepts, I set this equal to 0 and I can factor out an x squared, right? Now, that quadratic in the center, you could actually use the quadratic formula to find the solutions, couldn't you? But let's try the synthetic, because the synthetic should also work, right? If it breaks down, we should be able to do it. So synthetic, what are the numbers we're going to use? We have a 1 here and we have a 1 here, right? So what's our list? Plus or minus 1, that's it, right? Our list is simple. So we try synthetic using 1, -3, 1. And then let's try 1 out here. And when we do that, we get 1. Let's see, 1, that's -2, -2, and -1. That's not 0, right? Then we try -1 on the outside. 1, -3, 1. So we try that. See, -1, it's -4, and then that's 4, and that's 5. That's not 0 either. And we've exhausted the list. And the reason is because the solutions to that, okay, are not rational numbers. They're irrational. And so if we were forced to do this problem, what we would do is this. We would say, okay, here we have an x-intercept, 0, and it bounces here, right? Because we got x squared. But to do this, what we would have to do is use a quadratic formula. We would say that x is equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. You understand what I'm doing there to find the solutions to this? This would give us 3 plus or minus the square root of, let's see, 9 minus 4, that's 5, root 5, then all over 2. And this gives me 2 answers. This gives me 3 plus root 5 over 2. And then 3 minus root 5 over 2, which I understand we could get the decimals for these, right? But these are our x-intercepts, right? This is where we hit the x-axis at these 2 values. My question now is, do we cross or bounce there? Right? Do we cross or bounce? What do you think? Cross? Why cross? Yeah, so there's 2 answers, right? So watch, this is kind of crazy, but look at this. What we're saying is that this actually does factor, okay? It does. It factors to b. Well, here's what I can tell you. X minus that first one, and then x plus that other one. I'm sorry, minus that other one. Think about that. If you take x and you replace this x with that answer, this minus this, it'll kill each other off and we'll get 0, right? Or in other words, if I set this equal to 0, I get that answer. And if I set this equal to 0, I get that answer. So this is in fact 2 of the factors. And so the powers on those factors are 1s. And so we should cross there. All right. So I just wanted to show you that as nice as this whole synthetic division, rational 0 test and stuff is, it's not like it doesn't save you all the time, right? There are some things we cannot do that you cannot solve with this. Okay, it's 2:31, but there's really, the next thing we're going to go into next class is rational functions. So I want you to just take those homework problems I gave you, work on those. We'll come back and then we'll graph rationals. Rational functions are the hardest functions to graph by hand until you get to calculus when you have to graph other stuff. But we're going to graph in here three more types of functions: rational, exponential, and logarithmic. Those are the three remaining functions. And rationals are the hardest because they just have so many steps to them. So many things you have to pay attention to. So that's going to be it for today. I'll put the problems back up there in case you needed them. There they are. Any questions at home?
I think I'm good. Thank you so much, Professor.
no
Everything was
problem.
pretty well explained today. I was able to follow along.
Okay, good, because this will be a big part of the test. It's just, you just
Okay.
have to be careful, right? Just make sure you're not making any small sign mistakes.
Yes, sir.
Okay. All right.
Sir, I had to log in my phone because my computer died.
Yeah,
But I
yeah.
guess it's the class.
Are you good? Juan?
Yes, sir.
Okay.
All right.
All right, sir. We'll see you.